Our planet is a blue planet, a world of water. From space it shimmers, a beautiful azure marble suspended in the vast blackness of the cosmos. Most of this blue is our oceans, vast and deep, holding secrets we are only just beginning to understand. We have explored the moon more than we have explored the deepest parts of our own seas. Down there in the crushing dark lies a world so alien, so different from our own, that it might as well be on another planet. It is a realm of mystery, a place of profound silence and immense pressure, where sunlight cannot reach and strange, wonderful creatures make their home. But this world is not just mysterious because of its darkness or its inhabitants. It holds a peculiar secret, a phenomenon that has puzzled scientists and sailors for generations. Imagine a place where sound itself seems to vanish. To understand this mystery, we must first picture the ocean not as one uniform body of water, but as a layered cake. Each layer has its own character, its own temperature, its own density. Near the surface, the sun warms the water, creating a comfortable mixed layer where much of marine life thrives. But as you go deeper, the sunlight fades, and the water becomes colder, and colder still. The shadow zone is not a physical place you can touch, like a reef or a trench. Instead, it is a specific depth, a band of water that exists because of these changing layers. It is a region where sound waves, for reasons we shall soon discover, find it very difficult to enter. Think of it like a real shadow, but for sound instead of light. If you stand behind a large building, the sunlight cannot reach you directly, and you are in shadow. This special zone is typically found starting at a depth of around 600 to 1,500 meters below the surface. Its exact depth and thickness can change depending on the time of day, the season, and the specific location in the ocean. In warmer tropical waters, the change in temperature is more dramatic, so the shadow zone can be more pronounced. It is a dynamic, shifting feature of the ocean's architecture, a silent belt that girdles the entire globe beneath the waves, a hidden world within a world. On land, sound travels through the air. We are so used to it we barely think about it. In water, however, sound is a completely different beast. Water is much denser than air, about 800 times denser in fact. This means the molecules are packed much more closely together. When a sound is made underwater, a whale's call, a submarine's engine, or even a pebble dropping, it creates a pressure wave that pushes these tightly packed water molecules against each other. This is what a sound wave is. Because the molecules are so close, they transfer this energy very efficiently, very quickly. As a result, sound travels much, much faster in water than it does in air. On land, sound moves at about 343 meters per second. In the ocean, it zips along at an incredible speed of about 1,500 meters per second. That is more than 4 times faster. This is why whales can communicate over such vast distances. Their songs are not just beautiful, they are incredibly effective, traveling for hundreds, sometimes thousands of kilometers across the ocean basin, a testament to the power of underwater acoustics. Now, let us bring these ideas together. We have sound, a traveler that changes its speed based on temperature and pressure. And we have the ocean, a world of layers with different temperatures and pressures. When sound travels from one layer to another, something remarkable happens. It bends. This bending is called refraction. You have seen this effect yourself. If you put a straw in a glass of water, it looks like it is bent at the surface. The light is refracting as it moves from the air to the water. Sound does exactly the same thing in the ocean, bending as it moves between layers of different temperatures. Near the surface, the water is warm, so sound travels quickly. As a sound wave from a surface ship travels downwards, it enters the colder water below. Moving from a warm, fast layer to a cold, slow layer, the sound wave bends downwards away from the surface. This continues as it goes deeper and the water gets colder. The sound waves are constantly being pushed downwards, away from the source. But remember, there is another force at play: pressure. As the sound wave goes deeper and deeper, the pressure becomes immense. This increasing pressure starts to make the sound travel faster again. So you have a tug of war. The decreasing temperature is trying to slow the sound down and bend it downwards, while the increasing pressure is trying to speed it up and bend it upwards. At a certain depth, the effective pressure becomes stronger than the effective temperature. At this point, the sound waves that were bending down start to bend back upwards, towards the surface. This is the magic that creates the shadow zone. Let us delve a little deeper into the science behind this beautiful phenomenon. The key player is a layer in the ocean known as the thermocline. This is not a single line, but a region where the water temperature changes very rapidly with depth. Above the thermocline is the warm, sunlit surface water. Below it is the vast, uniformly cold, deep ocean. It is within this thermocline that the most dramatic bending of sound occurs. A sound wave entering this zone is like a car hitting a patch of ice. Its path changes suddenly and dramatically. The steep temperature gradient acts like a powerful lens, refracting sound downwards. The speed of sound in the ocean reaches its minimum point at a specific depth. This depth is called the axis of the SOFAR channel, which stands for sound fixing and ranging. This is the point where the battle between temperature and pressure finds a delicate balance. Here, the water is cold, which slows sound down, but the pressure is not yet high enough to speed it up significantly. It is the slowest point for sound in the entire water column. This axis of minimum speed is typically found at the bottom of the thermocline, often around 1,000 meters deep. The shadow zone is located directly above this SOFAR channel axis. Sound waves originating from near the surface are bent downwards, towards the region of slower sound speed in the thermocline, but they are bent so strongly that they pass right over the area just below the surface layer, diving deep before they are eventually bent back up by the pressure below the SOFAR axis. This creates the shadow where direct sound from the surface is absent. A submarine hiding in this zone would be almost undetectable to sonar from a ship directly above it. The ocean is not a silent world. It is filled with a symphony of sounds. Clicks, whistles, groans, and songs. And the greatest composers of the symphony are the great whales. For creatures like the humpback whale or the colossal blue whale, sound is everything. In the vast, dark expanse of the ocean where sight is limited, sound is their way of seeing, of speaking, of finding a mate, and of navigating the globe. Their powerful, low-frequency songs are designed to travel enormous distances, carrying messages across entire ocean basins. But even for these masters of acoustic communication, the shadow zone presents a challenge. A whale singing near the surface might find that its song cannot be heard by another whale that has dived deep into the shadow zone, even if it is relatively close by. The layers of the ocean can effectively block their conversation. To overcome this, whales have become masters of the ocean's acoustic landscape. They are known to dive to specific depths to make their calls, using the ocean's layers to their advantage. By diving below the shadow zone and into the SOFAR channel, their songs can get trapped in the sound channel and travel for unbelievable distances with very little loss of energy. They seem to have an innate understanding of ocean physics that we are only just beginning to grasp with our advanced technology. A mother whale might use the shadow zone to hide her calf from predators like orcas. By staying within this quiet zone, their sounds are muffled, making them harder to detect by hunters listening from above or below. It is a natural cloak of invisibility. For as long as humans have sailed the seas, we have sought to master them. In the modern age, this quest has taken us beneath the waves, into the world of the submarine. For a submarine, the primary goal is to see without being seen, to hear without being heard. Silence and stealth are the keys to its survival. And in this silent, deadly game of hide-and-seek, the shadow zone is the most important piece of terrain on the entire battlefield. It offers the ultimate hiding place, a natural sanctuary from the prying ears of surface ships. A commander's understanding of this zone is paramount. A submarine captain can intentionally guide their vessel into the shadow zone to become acoustically invisible to surface sonar. A warship on the surface might be actively searching, sending out powerful pings of sound, listening for an echo. But if the submarine is lurking in the shadow zone, those pings will be bent right over it. However, the shadow zone is a double-edged sword. While it provides excellent cover from listeners above, it also makes the submarine deaf to what is happening on the surface. To overcome this, submarines are equipped with highly sophisticated listening devices, called hydrophones, which can be towed on long cables. The constant cat-and-mouse game between surface ships and submarines has driven much of our scientific understanding of underwater acoustics. Navies around the world have invested heavily in mapping the ocean's thermal layers and predicting the location of the shadow zone in real time. This military need has, in a fascinating twist, provided oceanographers with invaluable data, helping us to understand ocean currents, climate patterns, and the behavior of marine life. The world of the shadow zone, often beginning in what is called the twilight zone or mesopelagic zone, is a realm of incredible wonders and surprising truths. The pressure here is immense. At a depth of 1,000 meters, the pressure is about 100 times greater than at the surface. It is equivalent to having the weight of a large van pressing down on every square inch of your body. Yet, life thrives here. This is also a world of living light. Since sunlight cannot penetrate these depths, many creatures have evolved to create their own light through a chemical process called bioluminescence. The darkness is punctuated by the flashes, glows, and shimmering displays of fish, squid, and jellyfish. One of the most astonishing phenomena associated with these depths is the deep scattering layer. They had discovered a massive, dense layer of living organisms, trillions of small fish, squid, and crustaceans that migrate towards the surface every single night to feed and descend back into the darkness of the shadow zone every morning to hide from predators. The study of the shadow zone and the deep ocean it inhabits is far more than just an academic curiosity or a military necessity. It is fundamental to understanding the health of our planet. The oceans are the Earth's heart and lungs. They regulate our climate, absorb carbon dioxide, and produce more than half of the oxygen we breathe. The deep ocean plays a critical role in these processes, acting as a vast reservoir of heat and nutrients. By studying how sound travels through these layers, we can learn about ocean temperatures and currents on a global scale, providing vital data for our climate models. This knowledge also helps us to protect the incredible life that calls the deep ocean home. Furthermore, the deep ocean remains a vast, untapped source of discovery. We know that life can exist in the most extreme conditions, and the unique creatures of the Twilight Zone may hold secrets that could lead to new medicines, new materials, and new insights into the very nature of life itself. To explore the Shadow Zone is to push the boundaries of human knowledge, to shine a light, however faint, into the largest and least understood habitat on our own planet. And so, our journey into the ocean's silent secret comes to a close. The Shadow Zone is a perfect illustration of the elegance and complexity of the natural world. It reminds us that there are still great mysteries to be solved, still wonders to be seen, and still silences to be heard. We must continue to listen, to explore, and to protect this magnificent blue heart of our world, for its health is ultimately our own.